So understanding that lactate response is really important to us, and it starts to establish for us the first of these exercise domains and how this is then linked to oxygen uptake. So to help us with this, we're going to go back to a paper published in 2007. This is from Annie van Hatterlo and Mark Burnley. And it's a really important representation because it explains for us about exercise domains. And they write this: on the basis of the characteristic blood lactate and oxygen uptake responses during constant work rate exercise, 3 exercise intensity domains have been defined: moderate, heavy, and severe. The boundary between moderate and heavy domains can be established during incremental exercise using the lactate threshold, which I've been terming lactate turn point, or its gas exchange equivalent, the gas exchange threshold. They're both fundamentally identifying the same point. This threshold is important because it demarcates work rates for which a VO2 slow component is present in the heavy and severe exercise from those which is not. That would be in moderate. The boundary between heavy and severe exercise signifies the highest work rate at which a steady state can be attained. Work rates above this boundary result in VO2 and blood lactate rising as a function of time until the VO2 max is attained, with exhaustion occurring thereafter. So from the previous data, if we just flip back, we've got our little boundary here. So we're saying, I'm going to go to this one here, maybe it makes it easier, anything below 15 kilometers an hour, we know is going to fall in the moderate exercise domain. And what Van Hatterlo is stating in that paragraph is in the moderate domain, a steady state is attained, both in blood lactate, in VO2, and therefore by definition in heart rate, cardiac output, and stroke volume. But once we move beyond this point here, what we start to develop is what is called a VO2 slow component. And I'll explain how the slow component works, but it has ramifications on the attainment of steady state. It has ramifications in terms of muscle fiber type recruitment. And the further we go beyond this point, and as we drift into the severe domain, we no longer have the ability to maintain a steady state, and VO2 and blood lactate will rise inextricably to the VO2 max. And we can see this here in this schematic, which is taken from Paul and Jones's review paper in Comprehensive Physiology. So this is the GET, so this is what you see in terms of the blood lactate response. It's the point where rate of appearance exceeds disappearance. It's just being identified here using gas exchange data. But exercise below this point in the moderate intensity domain, irrespective of what intensity you are working at in that domain, you will always reach a steady state. So you'll see in here, this is at rest, so this is a two-minute period at rest. We apply the workload, and what we get is this characteristic rise in the VO2. So it's not an instantaneous rise because fundamentally the kinetics aren't instantaneous. We have to borrow some anaerobic energy, which is the deficit, and we reach a steady state that you can see here. This is at a lower intensity, but both are in the moderate domain. Once you go above GET, but below what's called the critical power, what you see is a much higher VO2 response. That's not surprising because this would be at a higher exercise intensity. But notice, and it's not easy to see here, but it is visible. The VO2 rises, again, it's not instantaneous. And you'll notice it starts to level out. But then can you see, if you just follow the trend line, it just accelerates a little bit, it rises. And that is the start of what we call a VO2 slow component. If we go into the severe domain, so this is above critical power but below the VO2 max, the VO2 rises and keeps rising. You never get a steady state. These two examples here are exercise which is fundamentally being performed as close to VO2 max as possible, and somebody may just be stopping, for example, just to fatigue. But you can see that you never get a steady state if we're above critical power but below VO2 max. So you can understand, without really having any underlying physiological appreciation, you can understand there are 3 distinct biological responses taking place: a steady state, a non-steady state, and a steady state that comes with this additional cost of the start of the development of this, what's called the VO2 slow component. And so if we look at this, which is taken from Harry Rossiter's group, and what you can see here is this is against exercise time on the x-axis. I've taken those off because of the way I've edited the graphs. And so what you've got here, this is this is time, so this is the resting data here, and this is in the moderate domain. So here we get the application of the external load. The VO2 doesn't rise instantly, but the ATP turnover rate of the tissue rises instantaneously. So what we're doing is we're trying to match fundamentally the physiological response to the imposed external load. And so what happens is the VO2 rises and eventually reaches a steady state. When we stop exercising, we go into the recovery, so we develop what's called an EPOC. So it's the excess post-oxygen consumption. And you can see here that the curve starts to level out. And what is fascinating about this is, if you record the EPOC, that is the area under this curve here, and map it against the area above the curve here, they're matched. So the amount of oxygen one burns, or sorry, not burns, the amount of oxygen one consumes in recovery from moderate intensity exercise is directly proportional to the amount of oxygen one uses at the onset of exercise for moderate intensity exercise itself. Now, if we go a stage further and we look now, this is from the same paper from Harry Rossiter. This time what you'll see is the same principle. So here we've got our 6 minutes of exercise, but now this is in the heavy domain. So what happens is the same thing that we saw previously. You've got this period of rest. We've got the external loads applied, so you get an immediate internal response. That's the ATP turnover rate increases immediately, but other biological systems have to play catch up. So the VO2 rises in this kind of what we call this bi-exponential response. It starts to level out, and then it gently rises again. So we get in this VO2 slow component. This line here represents where the VO2 theoretically should have leveled out at, had a steady state been attained in the traditional idea of 3 to 4 minutes. What we start to see is in the heavy domain, you're actually getting into the realm of about 6 to 8 minutes to reach a steady state. In the recovery, now it gets more complicated. The EPOC no longer matches the deficit. Why? Because you've not only had to borrow the anaerobic energy at the onset of exercise, the actual development of this VO2 slow component, that is the additional VO2 superimposed onto the VO2 that was anticipated to be consumed at that workload, has to be added on and has to be basically recovered. So the EPOC exceeds the deficit. So the slow component is really important, and we understand that the slow component is predominantly a function of the exercising muscle. It's predominantly the function of recruiting fast-twitch fibers, and the byproduct of that is things like lactate production, hydrogen ion production. It's changes in things like ADP concentration. It's changes in PCR concentration, and of course things like heat being produced. Fast-twitch fibers are prolific producers of heat compared to a slow-twitch fiber. So the slow component isn't the result of an increasing lactate concentration. It is a result of the fast-twitch fibers, and the fast-twitch fibers just happen to be producers of lactate rather than consumers of lactate. So what you end up with is kind of these exercise domains. I don't want to dwell on this one because I think there are perhaps some slight misnomers in here, but it's quite useful that we've got what's called moderate, heavy, and severe, and then they go into this kind of extreme boundary here. But I think the big three we want to focus on are these moderate, heavy, and severe. So moderate, it's up to the lactate turn point, the gas exchange threshold. And what we can do in this domain, we can really do prolonged periods of work. You know, you could be getting up to, 4 hours of work. In the heavy domain, so this is from the lactate turn point or gas exchange threshold to the critical power. And, it does very much depend upon the individual, but it's a pretty tough domain to be in. The authors here reckon 3 hours. I'm not at all convinced that is possible to exercise for that amount of time within here. But what is important is that this point here, 3 components, slow components evident after primary phase, steady state delayed by 10 to 20 minutes. And then the upper domain, which is severe, which is anything above critical power, and the VO2 will rise to that point of VO2 max.